Hello. In this video, we're going to be taking a look at the notes for AP Physics 1, Rotational Motion and Dynamics. Please remember to pause or rewind the video as necessary. Let's begin. Section 7.1, Extended and Rigid Bodies. Explain what it means to treat an object as a point-like. Explain what an extended body is. Point-like objects, we consider the size or shape or geometry of the object. Extended bodies, the size, shape, and geometry matter. You can think of a point-like object as a particle or something that could revolve around something else. Extended bodies are going to be treated like objects that have an axis of rotation that passes through them. Therefore, their geometry matters. What is translational motion? How does it differ from rotational motion? Translational motion means all the atoms in the object move together with the same motion in a straight line. That's pretty key right there. Rotational motion, all the atoms of the object make circles around some common center. They rotate. What is a rigid body? Is the human body a rigid body? Why? Think of the organism. Think of an organism that is a rigid body. A rigid body cannot change its shape. Humans and other animals change their shape all the time. You have different shapes when you stand, walk, sit, etc. But a tree, well, that's relatively rigid. Explain what is special about the point called the center of mass of an object. The center of mass is the location where if the object is set on a fulcrum, the object would balance at that point. Now CM, we're going to abbreviate center of mass as CM. The center of mass is also the point at which the object rotates around. And it is the point that makes the parabola if the object is in projectile motion but spinning around. Name an object whose center of mass is far on one side of the object. In other words, not near the center of the object. Explain why this object has a center of mass that is far on one side. Well, a good example would be a hammer. The metal head of a hammer is much heavier than the wooden handle. Therefore, the center of mass is closer to the metal head. Why is the object's center of mass sometimes called the center of gravity? The center of mass is the location where the weight force is applied to the object. That is why the two terms often get used interchangeably. Although they are not the same thing, the center of gravity is always located at the center of mass. A baseball bat lies on a table. Give a brief procedure that could be followed to determine the location of the bat's center of mass. Well, you could push the bat over the edge of the table slowly. When it begins to tip over, the center of mass is right on the edge of the table. Section 7.2, torque, a new physical quantity. What is an axis of rotation? What is the axis of rotation of a door? What is the axis of rotation of your arm? The axis of rotation is a line which all the atoms of a rotating object make circular motion. The axis of rotation of a door would be the hinges, and the axis of rotation of your arm would be your elbow. What is static equilibrium? An object in static equilibrium does not accelerate in any way. Translationally, rotationally, tangentially, centripetally, no acceleration at all. Now we have a picture here in which we have a force applied to an object right at that point here. And what we come to find is that we can take, there's two different ways to describe it. When we are trying to provide a torque which uses the Greek letter tau as the symbol, is equal to a perpendicular force times a distance. Now let's describe what this is. The torque is the tendency to cause rotation. F is the perpendicular force, and D is the what's called the lever arm distance. Okay, now the lever arm distance is the distance between the perpendicular force and the pivot. The pivot is the point of rotation or fulcrum, whichever word you choose to use. So this force right here is not supplying a torque. Rather, it is the perpendicular component of force that is able to twist and rotate this wheel. Similarly, if we looked at, instead of R, we looked at the perpendicular component of R, that is what the force here is really pushing on. And so either way, here's the angle theta, here's the angle theta. This would be R sine theta. This would be F sine theta. And the equation we have is R perpendicular times F, or perpendicular F times R, or simply RF sine theta. Now, instead of using R, I'm going to choose to use D. The radius vector is one way of describing it when it's a circle, but it's not always going to be so easily visible as a circular radius. So I'm just going to say D, the distance to whichever. So I'm going to write the torque equation as perpendicular force times distance. That is a pretty good unified way of knowing how to do that. And so the perpendicular force, just make sure you use and find the perpendicular component of force. And you'll see what I mean when we have to apply it. Okay, explain what a torque is. Well, again, the torque is an action that causes rotation. So just as a force causes an object to accelerate, so the force causes an object to change its translational motion, a torque causes an object to change its rotational motion. Is it possible for a force to be applied but no torque to be applied? Explain how. Yes. The force is applied directly at the axis of rotation, because at the axis of rotation, there is no lever arm distance, and torque at the pivot is equal to 0. Let's think about why. Perpendicular force times distance. If the distance is 0 at the point of rotation, then 0 times any force is going to be 0 torque. The other way is if the force is directed toward or away from the axis of rotation, meaning a parallel force, as opposed to a perpendicular one. Think about it this way. It would be like pushing parallel to a door instead of perpendicular to one. You're not really going to open up a door if you push parallel at the end of it or pull parallel at the end of it. You have to push or pull perpendicular to the plane of the door in order to rotate it. Is it possible for a torque to be applied on an object without the presence of an applied force? No. Force results in a torque. Name a tool that demonstrates the principle of torque. Explain how the tool is used to get more torque. Well, a wrench would be a good example. It gives you basically a greater radius due to the handle, which means greater radius, greater distance, more torque, more twistability. Easier to get off not as much force required to turn the nut that you're trying to tighten or loosen. Now, the torque activity on page 3, we can skip that for now. That's going to be done later in class. Section 7.3, Conditions of Equilibrium. Explain in words as simply as possible what conditions of equilibrium are. Well, it's basically when all forces are balanced. Forces up equal forces down, right equals left, but it also means torques are balanced too. Clockwise torques equal counterclockwise torques. Okay. So a couple of things to note here. Rotational, this is what's referred to as rotational equilibrium. Now, rotational equilibrium, we would set clockwise torques equal to counterclockwise torques. And don't forget about the fact that torque is a perpendicular force times distance. Okay, example 1. What mass should be placed at the question mark so that the system is balanced? Write a balanced torque equation and solve for the unknown mass. Well, there's the point of rotation right there. So I'm going to write this in blue. You've got mg, so I'm going to call this m1g. I'm going to call this m2g. And then this unknown weight would be m3g, where m3 is going to be our missing unknown mass. Okay, now, since m1 is 20 centimeters away, that would make this d1. m2 is 10 centimeters away, that would make this d2. And the unknown mass is also 20 centimeters away, that would make that one d3. So it's going to correspond to whichever force or whichever object is acting at that point. Okay, let's use our information. We have, now if we focus on the bar, so this is the bar right here, and if we were to twist it, whoops. Let me fix that. So we're looking for M3. Okay. There we are. Pull this out for a second. Okay, so you can see that M1 and M2, weight 1 and weight 2, are on the left side of the pivot point. Therefore, they would cause, since they're pulling down on that side, they would cause counterclockwise rotation. So there's 2 counterclockwise torques, 2 forces that cause 2 counterclockwise torques. Whereas M3, or weight 3 rather, is pulling down on the right side. That would cause a clockwise torque. What's helpful to do in these problems is identify that. These 2 here cause counterclockwise torques. This one causes a clockwise torque. And if you identify it in the picture, it's much then easier to set up in a calculation. So we have counterclockwise torque equals clockwise torque. There are 2 counterclockwise torques, so that would be M1g is your force. I'm filling out force times distance here, times D1 plus M2g times D2. So all of that is my 2 counterclockwise torques. And they're going to be equal to the 1 clockwise torque, which is M3g D3. Notice the g's will cancel because there's a g in every term, and you are looking to solve for M3, which means you have to divide away the D3. So it's M1 D1 plus M2 D2 over D3. Go ahead and plug into that. And there's no need to change the units, whether it's grams, kilograms, centimeters, meters, nanometers, who cares? It doesn't matter because of the fact that you are going to be canceling units, since the units exist on all terms and all parts of the equation. Therefore, whatever the unit is whatever the unit is, no need to change it. So M1 was 0.15 times its distance of 20, plus then you have M2, which is 0.10 times its distance of 10. Okay, and then distance 3 is also 20. Okay, so M3, okay, so 0.15 times 2 times 20, that would be 3. So we have 3 plus, and then on the other side over here, 10 times 0.10 would be 1 over 20, which would be 4 over 20, which would be 1/5, or 0.20 kilograms. Example 2. What is the net torque on the system, including direction? Well, let's go back to the bar. Right here, you can see the center of the axis is still the point of rotation, and you can see both masses are on the left side. They would cause counterclockwise rotation. There is no balancing on the right side of the axis of rotation. Therefore, you have what's called a net torque. Specifically, you have 2 torques that are contributing to that net torque, and both of them are counterclockwise. So the direction is going to be counterclockwise. So the net torque, which is counterclockwise torque, is going to be due to, we'll call this M1, we'll call this M2, and it's going to be M1 G D1 plus M2 G D2. Force times distance plus force times distance. Plug in. M1 is 0.1 times, let's focus on the distances here. So this would be D1 right there, and this would be D2 right there. Then the lever distance is always defined as the distance from the force applied to the axis of rotation. So 0.1 times 30 plus 0.05 times 20. And putting that in your calculator, you should get about 0.4 Newton meters counterclockwise. Okay, question is, where do we put a 0.20 kilogram mass so that it balances this system? Well, clearly it's going to have to be put on the right-hand side. You need a mass over here in order to balance it. But where do we put it? Here's the clue. In order to balance the system, this needs to contribute to the exact same torque. So to balance, we need 0.04 Newton meters of torque on the right side. So torque is equal to force, perpendicular force times distance, which means torque is this way equal to M3, this would be M3, D3 sorry about that, M3G, that's the weight, that's the force, times D3. And we're looking for D3 because it's saying where do you put it? So D3 is equal to the torque divided by M3G. The torque is 0.4 Newton meters over, we have the mass of 0.20 times 10, which would be 0.4 Newton meters divided by 2. To 0.2 newtons. You can see the newtons part cancels, and you would put it at 0.2 meters. So if I put it at 20 centimeters, which is right there, if we put it right there, it'll balance those two. Example 3. What masses should be placed at the question mark so that this system balances? Write a balanced torque equation and solve for the unknown mass. Well, these two weights would provide counterclockwise torques. So we have two counterclockwise torques. And this would pull in this direction. The weight at the end would pull in that direction, causing a clockwise torque. So we have one clockwise torque balancing two counterclockwise torques. So we'll call this mass 1, mass 2, and mass 3. There we go. So we have all your two clockwise torques balancing or equaling your one clockwise torque. So this is mass 1 times g times distance 1 plus mass 2 times g times distance 2, that would be those two together, equals mass 3 times g times distance 3. And we're looking for the unknown mass, so we're solving for M1. So let's go ahead and subtract this over and then divide by GD. And mass 1 will be M3 GD3 minus M2 GD2 over GD1. So we mass 3, we have 0.1 times G is 10 times D3 is 30. Again, I'm going to leave it all in centimeters because the unit of centimeters will cancel, so it's fine. Minus M2, which is 0.20 times 10 times, that one would be 10 centimeters from the axis of rotation. Divide that by G is 10, and that would be 20 centimeters away. Okay, so the first one we have 0.10 times 10 times 30 is 30, minus 0.20 times 10 times 10 is 20, all over 10 times 20 is 200. 10 divided by 200 is 0.05 kilograms. That would be the unknown mass you put here. Example 4. What is the net torque on this system, including direction? Well, both weights are equidistant, but you can clearly see the one on the right is twice as heavy as the one on the left. Therefore, you would expect the whole system to rotate in the clockwise manner. So the clockwise is the direction. What will the net torque be? Well, this weight causes the torque. So this would be the causing torque. That would make this the opposing torque. Just like net force is causing force minus opposing force, net torque is causing torque minus opposing torque. Call this mass 1 over here, mass 2 over there. All right. Let's see. Okay, so your net torque, that's going to be your causing torque minus your opposing torque. Your causing torque will be m2g times distance 2 minus m1g times distance 1. Both distances are the same. Okay, but m2 is twice as heavy. So we're going to go 0.1 times 10 times 30 minus 0.05 times 10 times 30. And in this case, since I'm not solving a balanced torque problem, I should write the units of distances in meters. For balanced torque problems, you can leave it like I did in the previous problem because it will cancel. But here, the only thing on the other side of the equation is the net torque. So it would be 0.30 and 0.30 on both sides. So 0.1 times 10 times 0.30 is 0.30 minus 0.05 times 10 times 0.30 would be half, which would be 0.15 Newton meters. Okay, and then finally, where should a 0.15 mass be placed to balance the system? Well, first of all, the whole system right now is leaning towards the clockwise direction. So you want this to cause a counterclockwise torque to balance it. So the net torque so far that we have is 0.15 Newton meters clockwise. Okay, to balance this, we need the same, but counterclockwise. Okay, so net torque equals force times distance. That's mass times g times distance, and we're looking for where, so we're solving for distance. Distance is equal to the torque divided by mg. It's going to be the same magnitude because it has to balance. Same magnitude as the other net torque divided by 0.15 times g is 10. Okay, and it should be placed at 0.1. And the only way to do that would be put it right here, 0.1 on the left side to create a counterclockwise torque. So it's 0.1 meters to the left of the pivot point, or point of rotation, or fulcrum, whatever you want to call it. Okay, walk the plank example. Consider a wooden plank set so that the length hangs over the edge of a building as shown. If a person walks out onto the plank may tip over and the person will fall. You will model this situation with a meter stick and place the plank in place of the plank and a mass in place of the person. Well, let's go ahead and solve this together, and we'll revisit this in class. Okay, so the mass of the plank, about 80 grams or 0.8 kilograms. Mass of the person, about 20 grams or 0.02. And the pivot point is at about 0.55. So you can see it's placed about 5 centimeters. Here's the halfway point. It's placed, the edge right here is where it would pivot, and that's at the 5 centimeters past the midpoint. Okay, so go to our picture. Let's zoom in our picture. The forces acting on this thing would be the weight of the person. So M times G times, we'll call this distance X. This is our mystery distance. That's what we're looking for. And the center of the meter stick provides the center of mass. So M times G times D, where this is distance D from the center of the meter stick to the edge of the table, which is our pivot. Okay, so this contributes a counterclockwise torque. This contributes a clockwise torque. So counterclockwise torques equal clockwise torques, or mgd equals mgx, and we're solving for x. Okay, now m is the mass, m1 is the mass of the meter stick, m2 is the mass of the person. You'll notice that the g's cancel because it's on both sides, and so it's m1 times d over m2. Okay, so the mass of the plank is 0.08 kilograms times 0.05 meters. That's the distance. 0.55 meters is the location of the pivot, but the distance is 5 centimeters. The 50 centimeter mark is 5 centimeters from that pivot. So we're putting 5 centimeters in here. Divided by M2, which is the mass of the person, 0.02 kilograms. And the person can walk out a maximum of 0.2 meters, or essentially, if the edge is at the 55 centimeter mark, they can go no more than 0.75 or it'll tip over. That's 0.20 meters beyond the pivot. We'll try it in class and see how the prediction holds. Bridge support example. Consider a bridge with two supports. An object rests on the bridge somewhere off center. You are to determine the force that each support exerts on the bridge. You will model this situation with a long piece of wood and a known mass. Okay, we'll model this in a certain way in class, as one lab we're going to do, in which you're going to use a long board to lay on top of and help determine what the location of what your center of mass is. Okay, so what we'll do in this one is we'll choose the one pivot to be the fulcrum and the other pivot to be something that we know the force from that support. Because these, if you draw the forces acting on this thing, you have the force from the beam itself, which is big mg. You have the force from the little one, which is little mg. And then you have the force 1 from support 1, and then you have force 2 from support 2. Okay, so those are the forces that are acting on the bridge. And right now it says choose one of the supports to be the axis of rotation and then write a balanced equation for it. So let's just go ahead and I guess we'll make the axis of rotation at the left end, which means you do not count force 1 in your equation because the torque at force 1 is 0 because there is no lever distance at that point. But you do have, let me see, this and this would cause clockwise torques. This causes a counterclockwise torque. So we have one counterclockwise torque, and we have two clockwise torques. And so our equation would look like clockwise torques equal counterclockwise torques, and we're looking at mg times, I guess, d1, since this is m1, plus big mg, and then the bridge, I guess, would be the halfway point, so half the length. Since it's at the meter point, it would be half a meter. And we're going to set that equal to the one counterclockwise torque, which would be the force from the support. That would be the force 2 times the entire distance 3, which is up, going that way. Okay, so we're looking for, we're determining the force that supports each exerts on the bridge. So what we basically want to do this one at a time, letting each axis be the, each support, be the axis of rotation. So starting with the left end being, we have this, and we would solve for F2. mgd1 plus mgd2 all over d3. Okay, let's plug in. Let's see. Little m is the mass of the mass on there, the mass of the object, so that's 0.05 times 10 times the object is 0.2 meters away from the left end, because that's our axis of rotation, plus the entire bridge is 0.08 times 10, and the halfway point would be 0.5, which would be the middle, or the half a meter mark. And then D3 is all the way at the other end, that's 1 meter. So force 2, let me just write it down here, I'm kind of running out of room. So force 2, so we're going to go 0.05 times 10 times 0.2. Force 2 would be 0.1 plus 0.08 times 10 times 0.5 would be 0.4. All that divided by 1. Okay, so force 2 would be half a Newton. Now, since the mass is located closer to force 1 from support 1, you would expect the force from support 1 to be a bit greater. Let's verify that. We're going to do the exact same thing. The only difference is we're going to let support 2 be the axis of rotation and see how everything plays out. Now, if we do that, I kind of have to erase the clockwise and counterclockwise because you now have to essentially start over. If this is now the axis of rotation, you eliminate force 2 from your torques because you have no torque at the axis of rotation. You would have 1, 2 counterclockwise torques and 1 clockwise torque. If you picked up on the pattern, it's exactly the opposite of what we set up before. We had 2 clockwise torques equal 1 counterclockwise. Now we have 2 counterclockwise torques equal 1 clockwise. So it's going to be little mg times d1 plus big mg times d2 equals the 1 clockwise torque of F1 times d3. Okay, you're solving for F1. Same as before. So F1, we're going to have mgd1 plus big mgd2 all divided by d3. Little mass again was 0.05 times 10 times. Okay, now the little mass is 0.2 meters from this end. That would make it 0.8 meters from that end. So 0.8 plus 0.08 is the mass of the bridge, times g times 0.5 being that the center of mass is at the halfway point, all divided by the fact that support 1 is 1 full meter away, d3 is 1 full meter away. 0.05 times 10 times 0.8 would be 0.4 plus 0.08 times 10 times 0.5 was also 0.4 over 1 meter. And it's 0.8 newtons, which falls in line with our predicted model. If you have a mass that's placed closer to support 1, you would expect support 1 to apply more force to balance it. We will simulate this particular example with a center of mass lab in class. Okay, we'll also be taking a look at this one in class too, so go ahead and skip for the time being. Section 8.1, Rotational Kinematics. A circle can be split into pieces called degrees. There are 360 degrees in a circle. Well, a circle can also be split into radians. There are about 6.28, in other words, exactly 2 pi radians in one circle. Okay, so we're going to be using that to be able to convert. 2 pi radians is essentially 1 complete circle or 1 revolution. 2 pi radians and 1 revolution. We're going to keep that in. We're going to keep that in our hip pocket because we're going to need that. Angular displacement, explain angular displacement, angular velocity, and angular acceleration. Give basic examples. Well, angular displacement is the angle in radians an object rotates through. The variable for that is theta. Angular velocity is the rate at which angular displacement changes. Now this is going to be in a unit of radians per second, or sometimes it's in revolutions per second, or sometimes it's in the revolutions per minute, although radians per second is the proper unit. These are also other ones that you will tend to notice. The unit for it, well, those are the units. The variable for it is the Greek letter omega. Omega kind of looks like a, I don't know, an italicized W, a cursive W. Okay, but it's not. It's the Greek letter omega. Think of angular velocity as how fast something is rotating, how fast something is spinning. Angular acceleration refers to spinning faster or slower. It's the rate at which angular velocity changes. The unit should be in radians per second squared. Okay, write the equation that relates each linear quantity to its rotational analog. Well, you've got angle theta, radius, and an object has gone from here to here along length L. But I'm going to give this a new variable. I'm going to call it S. That's usually pretty in line to what they use on the AP exam and on the formula sheet, and I'm just going to keep it consistent. And the equations are actually all written down below. I'm just going to rewrite this. S equals R theta. Now the tangential speed at any point can always be, that would be V. V is the tangential speed, the speed tangent to the object at any point around the circle, can be related to how fast it's spinning or rotating through the radius, how far it is from the center. And so V is equal to R omega. I'm just reordering the two terms here. And then finally, the tangential acceleration is equal to R times alpha. Alpha, I forgot to mention that earlier. Alpha is the angular acceleration. Okay, so what we're going to do in this table is we're going to take each of these equations that we know from translational, meaning linear kinematics, and we're going to translate all of them into the rotational counterparts. So every time we see an x, we're going to replace it with theta. Translational or linear position, angular position. Linear displacement, angular displacement. So anytime we see an x, we're going to replace it with theta. Anytime we see a v, we're going to replace it with omega. Linear speed, translational speed, that would be angular speed. Anytime we see an a, we're going to replace it with alpha. Okay, let's give it a try. So up here, we have x equals vt plus x naught. So that would be theta equals omega t plus theta naught. This second equation says v equals at plus v naught. That would be omega equals alpha t plus omega naught. Third equation says x equals 1/2 at squared plus v naught t plus x naught. Well, that would be theta equals 1/2 alpha t squared plus omega naught t plus theta naught. Last equation says v squared equals 2ax plus v naught squared. So we have omega squared equals 2 alpha theta plus omega naught squared. Okay, the bike wheel activity, go ahead and skip this for the time being. We'll be taking a look at that in class. And go ahead and skip the gear activity. We will do this as an activity together in class as well. Example. The speedometer in your car is attached to the axle of your car, not directly to your car's wheels. A friend of mine with a car with 20-inch wheels and the speedometer was calibrated for these wheels. That means when the speedometer measured 60, the car moved 60 miles per hour. My friend replaced all of his wheels with 24-inch wheels, but didn't change the speedometer. Now when his speedometer measures 60, what was his car doing? Okay. So this is a real situation. Many people these days, especially when they get trucks, ended up lifting their vehicles and putting larger tires instead of the factory-made tires. And that if you don't recalibrate the speedometer, that messes with the actual speed that you're going. So let's take a look at this example. His car is actually going 72. And here's how we can find that out. If V equals R omega, then V and R can be the speed and the radius. Okay. Then we get 60 now equals omega times 20. That would be for a 20-inch wheel. Okay. So omega equals V over R, and it's 60 over 20. And so you get 60 miles per hour divided by 20 inches is 3 miles per hour per inch would be the units. Now we're going to use the exact same thing. Now you're rotating it the same way because the axle is the same size. The axle didn't change. So, but the wheels are just bigger. Okay. So if we use our equation V equals R omega, you're using the same omega, but with a different R, 24-inch wheels. So the same 3 times the 24 gives us 72 miles per hour. 12 miles per hour difference, just with slightly bigger wheels. Section 8.2, 8.3, and 8.4 all relate to the concept of net torque and ways to write Newton's second law. So now Newton's second law tells us that a net force causes a mass to accelerate. Well, we're now going to encounter rotational version of Newton's second law, in which case if a net force causes a mass to accelerate translationally, a net torque causes a mass to rotate faster or slower. So I is what's called the rotational inertia and is very analogous to mass, but from a rotational point of view, just as alpha is analogous to acceleration. Let's take a look in more detail. Is a torque required to be present for an object to rotate? Careful how you answer this question. Make a statement about how torque relates to rotational motion. No, torque is needed to change the rotation. Explain what rotational inertia is. What does it feel like if an object has lots or little rotational inertia? Well, rotational inertia is how hard it is to change an object's rotation. Just as though mass is indicative of the object's linear inertia, if you really want to refer to it that way. And the bigger an object is refers to how hard it is to change an object's linear or translational motion. Well, I is the rotational counterpart to that. If an object has lots of rotational inertia, it's hard to get it rotating, or it's hard to stop it from rotating. The symbol, the variable is I, and the unit is kilogram meters squared. What does it depend on? Well, it depends on the mass of the object, and it depends on how far the mass is distributed from the axis of rotation. We're going to see this a little bit later on, but I is proportional to mr squared. We talked about these a moment ago. Newton's second law of rotation states that alpha, the angular acceleration, is caused by a net torque, just as translational acceleration is caused by a net force. Torque causes an object to change its rotation. F causes an object to change its translational motion. I is how difficult it is to change an object's rotation. Mass is how difficult it is to change an object's translational motion. Alpha is the rate at which the rotational motion changes. A is the rate at which translational motion changes. Again, just a side-by-side comparison between translational and rotational properties. Okay. In the yo-yo activity, a yo-yo of mass m and 2 radii, the inner axle of the yo-yo and the radius of the outer shell is big R. So the inner axle is little r, the outer shell is big R. The yo-yo is released from rest, causing it to fall and unroll with acceleration A. Draw all the forces on the yo-yo, determine the forces at which the point is applied. Well, you have the weight from the yo-yo, which would be mg, and then you've got the tension in the string that is pulling upwards as the yo-yo unwinds. So mg is down from the center of mass, tension is up and emerges from the left or right side at the inner circle. Briefly describe a procedure that would allow you to measure the acceleration of the following yo-yo. Explain what you did, how you measured, citing equations, and how you would use your measurements to find the acceleration. We will do this activity similarly, except instead of using a yo-yo, we're going to be using a roll of toilet paper, but it's a very, very similar idea. Well, we can measure the length of the yo-yo string, okay, then release the fully wound up yo-yo and time how long it takes for it to reach the end of the string. The string length is x, time is t, plug it in and solve for acceleration, and x equals 1/2 at squared. Okay. So in order to write two equations for this, we would essentially have one equation for translation, which would be the weight minus tension equals ma, accounting for the fact that we're accelerating downward, so the weight minus the tension equals ma. But you also, at the same time, the tension in the string is causing rotation. Therefore, tension causes a torque. So net torque equals I alpha, and it's tension times radius. Remember, guys, torque is force times distance. So the torque due to tension would be the tension, the force, and the distance of the lever is the radius, this right here, the little radius. So I should probably write it as little r, not big R, not to get it confused. So tension times little r equals I alpha. You would also need A equals R alpha to substitute for alpha. Okay, I'm going to go ahead and the rest of the problem here, we're going to go ahead and skip for the time being. Because again, this is part of a lab that we're going to do, but I'm walking you through some of the fundamental, just these are talking points that I want to make sure that you are familiar with. That way, when we put you in this lab scenario, you have an idea about how to proceed. Okay. Again, we're going to skip the bike wheel activity for the time being because this is a lab you're going to do. You're going to find the rotational inertia of a bike wheel. So we're going to hold off on this for the time being. And the very last activity over here, the falling meter stick, we are also going to skip, as this is also an activity we're going to be doing. So we have a lot of things that we're skipping essentially to a later time where we'll get to them. So again, please remember to rewind and pause the video as you need to, and thank you. In the next video, we'll go ahead and take a look at rotational energy and rotational momentum.